All right. Third one in this, I think it's going to come to 4 for this first part. It seems like it should be less, but anyway, now you see a lot here. Try to focus on just what's at the top. So now we're going to talk about that free energy. Remember, it can also be called available. Think of that a lot. Available energy. It's a measure of a system's instability. Okay, where am I pulling that out? Okay. Well, if we want to say how much available energy, well, that would be a measure of like how much that system would be unstable, like either releasing energy or it needs energy. It would be unstable. Okay. So that's where instability comes into play. And we're going to get into this equation down here, this Gibbs free energy equation, in a little bit, that's going to measure this spontaneity. Okay. So now, one other thing we need to say about free energy. Yes, it's a measure of the system's instability, or the measure of like how much energy is available, but it's also the tendency to change to a more stable state. So when we look at free energy, it's actually going to tell us, can it become more stable or less stable? And there's that instability again. So we're going to use that word spontaneity again. Okay. So for a reaction to occur spontaneously, what do we need to know about this? Well, two things. For a reaction to occur spontaneously, and I'm not talking about, everybody always thinks of spontaneous combustion, like you're sitting there and then boom, you're going to explode. Spontaneous, what does it mean? If a reaction can occur spontaneously, that means two things. One, no energy is needed. And two, for it to happen spontaneously, it must increase that entropy again. So must increase entropy. So after it happens, there's got to be more disorder, and you don't have to put any energy into it. So we go back to that, mysteriously exploding thing. There's a lot of things out there that have a lot of potential inside them. And if you don't have to heat it up at all, which that's very rare, because usually you have to activate anything. And we're going to talk about activation energy after we talk about all of this and how enzymes actually lower that. So most likely, like, think about a match. Do you ever get nervous just having like a pack of matches maybe in a drawer or something? And why? Because they can flame up. But what have you got to do to that match? You got to like start it up. Matches are actually an example of something that's very spontaneous. It can actually spontaneously erupt, but does that do it? Does spontaneous mean just going to happen out of the blue? No. Spontaneous just means no energy is needed. So it's going to release a lot of energy. So I want you to think anything that's spontaneous is going to releases energy. Okay, so keep that in mind also with that. Now, so what about a reaction that occurs unspontaneously? Well, let's look at the flip side of that. So if no energy was needed here, well, then an unspontaneous reaction is going to requires energy. Requires energy. So it requires energy input, right? And then must increase entropy. Well, this one, then if it's unspontaneous, okay, for a reaction to occur unspontaneously, energy needs to be added. So more order will result. Okay. All right. So here we're increasing, getting more disordered. Here we're going to put order. And again, I think about your bedroom. Okay. If you have to put a lot of energy into it to keep it orderly, that's a good example of an unspontaneous reaction. Okay. And in an unspontaneous reaction, again, energy is consumed. Okay, so your bedroom is actually stealing your energy from you to make it more orderly and all. It is. All right, so we have an equation, because math always can answer like anything, just about. And the equation here is called the Gibbs free energy equation, named after this guy Gibbs, which happens to look like a friend of mine. I remember like when I saw a picture of him, I was like, we were freaking out. My husband and I were like, oh my gosh, this is Gibbs. And we have a really good friend that looks just like him. And we're cracking. We call him Gibbs sometimes now. No, it's not Luke Gibbs. Okay, but It's another guy. And I don't know, maybe Luke Gibbs is a descendant of the guy that came up with this equation. Probably not, because Luke, you don't like math. Okay. All right. So getting off of that topic now. What is this equation? Delta G, okay, equals delta H minus T delta S. And T and delta S are multiplied to each other. Seems simple, right? And we are going to do plug and chug. We're going to put numbers into this, but we got to understand what this means. I'm actually going to start over here. Delta S is the change in, well, it's disorder of the system. So what is that word? It's the change in entropy. Entropy. Okay, change in entropy. So now you have a symbol for entropy, disorder. So if you have S and it's very high, then you're very disorderly. Okay, and if you're very orderly, and I think of some people like Elena Spates. So you're very orderly. Your notebook is very orderly. I would think of you as like very low S. You have, you're very orderly. Okay, you're not disorderly. Okay. Next one is T. T is temperature. It's got to be in degrees Kelvin. Remember, for those of you who forget, that's degrees Celsius plus 273. Okay. All right. This is going to be a value. Okay. This is going to be a value, obviously. And then delta H. Delta H is another word, and it's the internal energy in a system. Now, here's the thing. Delta H stands for change of energy. Okay, but I'm not writing that yet. Okay. And why? Because when people first came up about this and they were looking at living things, remember we said heat and light. So usually said, all of thermodynamics. They even like stress, heat. It's all about heat. Heat. It's like Marsha. It's all about heat here, But energy, we realize, can come in the form of electricity or sunlight or heat, many different forms. And that's why nowadays in biology, we talk about endergonic and exergonic. You're going to see those terms later on. But what does this delta H actually stand for? It stands for a weird word called enthalpy. Enthalpy. Okay. And that really does relate to heat, but in biology, we're going to even consider light maybe in there. And that's why we're not going to talk it all the time like it's not all about heat. So we're just going to say it's the internal energy of a system. So enthalpy is the change in the energy of a system. So we got entropy times temperature, subtract that from enthalpy, and that's what the available energy will tell us. Now remember, we said up here, available energy is a measure of a system's instability. Okay, is that system going to require energy or not? So when we figure out the delta G, that's going to say our available energy. Okay, our available energy, the change in the free energy. That's the energy that's now available to us. And wait till you see it, and you can probably see it already at the bottom. Let me try and cover that so we're not spoiling the ending here. Okay. This is the portion of the system's energy that can still do work. Okay. So delta G is what's left that can still do something. Kind of like what's left in the tank. Okay. Now, sometimes there's nothing left in the tank. Sometimes there's actually a negative value. It's kind of like owing money or something like that. Okay. What's that all about? Okay. So we have like a little statement, very important statement to use here. Okay. See, it starts. This equation is used to distinguish a spontaneous reaction from those reactions that require energy, or non-spontaneous reaction. Okay. So we figure all this stuff out, and then we can say whether this thing is going to go boom or if we're going to have to put a lot of energy into it. Okay. So this is a way of determining if something's going to require energy or if something's going to give off energy. Now, what would we really want to do? Do we really want to put energy into things? No. We don't want to spend energy like we don't want to spend money, right? We'd rather have money given to us, right? So we'd rather have energy given to us. So keep that in mind. So if we do this calculation and our delta G comes out, it can come out one of three things. Come out negative value, a positive value, or zero. Okay, let's start with zero since that seems to be easy. If you do all these calculations and delta G comes out to zero, then what you're looking at is basically something that's at equilibrium. Do you think living things ever get to that? We'll get back to that. Okay. Next thing, positive. If delta G, you do all these calculations and delta G comes out positive, then that means it's a reaction that's going to require energy, require a payoff. Okay. Okay. That's going to be something that's going to require work, going to require energy. Okay. And we call that endergonic. That's like the old endothermic. Remember endothermic? Now, this, and I still say the word endothermic. Therm just applied to heat, but endergonic means like it's more all the energies possibly out there, like electricity or wind or nuclear or heat or whatever, light. Okay. I still use the term endothermic, and I'm okay if you use endothermic. Endergonic, think of them as synonyms. Okay. But this is really encompassing all types of energy. This is just encompassing heat. So if something is positive delta G, it's going to require energy. It's going to require some work, okay? And then finally, there's the negative ones, okay? Negative. Negative means it's like it's going to give you energy, if anything. And I know you want to think positive. Isn't that positively giving you something? No. Negative, okay? Because the energy is being released, okay, out of the reaction. Okay, so it's coming out of the reaction. It's exiting the reaction. That's exergonic. That's the newer version of exothermic. Same thing. Again, you're allowed to use these two terms interchangeable, as the same as here, exer, but the gonic encompasses more energy. So when you do a formula like this, if it's zero, that system is at equilibrium. If it's a positive value, that system is going to require energy. And if it's a negative value, that system is going to give off energy, which is the system that you want. Well, we want energy, okay? We want things that are going to give us energy, like the sun, okay? All right, let's go on to our last page and let's see what I can get through this. Oh, this is a nice example, okay? So this example, okay, is photosynthesis. Or nope, rewind. This example here, glucose plus oxygen giving off carbon dioxide and water, this is respiration, right? This is respiration, cellular respiration. Okay, I'm just going to write respiration. Glucose has more free energy. It would have a positive or negative delta G. So it has a lot of available energy. It's very less stable, so it's very disordered. Okay. It has a greater capacity to do work. Okay. This side of the equation has less free energy that's available. It's more stable. It has less capacity to do work. So now, this is the other thing I want you to think. When you eat and breathe, do you get warm? Does your body get warm? It does. And you know why? Because as you eat, these bonds are getting broken. Okay. This is a very stable molecule, glucose. Okay. It has a lot of bonds in there. Remember that? And that potential energy in there. Okay. So it's going to be actually have like a lot of ability to do work. So when you eat, it's giving off energy. Now, yes, you get a little warm after you eat. Where's most of that energy going into? To form ATPs, which we'll get into later. Okay. But carbon dioxide and water, they're just like end results. They're very stable molecules. You can't break them down much more. I mean, carbon dioxide only has like 4 bonds. Carbon, 2 O's, 2 bonds to this. And water, we know this is just this, right? But glucose has like a whole bunch of bonds. I'm not going to draw the whole glucose molecule right now. These molecules are more stable. This is less stable. Okay, this has more free energy because it's tied up in those bonds. This has less free energy because there's not many bonds. Okay, this has a greater capacity to do work. That's why food makes us able to do work. And this one, less capacity to do work. So, overall, let's finish this up, hopefully, and I'm not going to be able to. Reactions want to move towards maximum stability. That's why we break down glucose and then our bodies are like satisfied. But we put that energy, sorry, you couldn't see that. The actions move towards maximum stability. That's what they want to do. And overall, we got to look at the delta G. We got to look at the final versus the initial minus the initial to get the overall delta G of this. All right. And I'm going to